As we discussed in an earlier video, for most densities f that one might think to specify for the error terms epsilon n in a random utility model, the integral that determines choice probabilities does not lead to a closed form expression for these probabilities in terms of the parameter vector theta. An important exception to this general rule is the so-called Logit family of choice models, to which we turn our attention in this video. The Logit family of random utility models is constructed by assuming that the errors are independent draws from a distribution with cumulative distribution function f of z is equal to e to the minus e to the minus z. Under this assumption, there is a simple and intuitive closed-form solution for the choice probabilities as given in the following theorem. The probability that decision maker n chooses alternative I is equal to e to the representative utility of that alternative divided by the sum of the representative utilities of all the alternatives. The CDF f that appears in this theorem is known as the Gumbel or type 1 extreme value distribution. As a corollary to this theorem, we discover that the difference of two independent Gumbel random variables is a standard logistic random variable. This figure plots the density at left and the cumulative distribution function at right for a Gumbel random variable. Notice that the density is not symmetric about 0, but when we take the difference of two independent Gumbel random variables, we obtain a standard logistic, which is symmetric about 0. By specifying the representative utilities v and j in different ways, the theorem from 2 slides back allows us to construct a number of popular discrete choice models for settings with more than 2 alternatives. Here we will focus on 2 of them. The multinomial logit model arises when all attributes are fixed across alternatives, so that v and j is equal to s n prime times gamma j. As we noted in an earlier video, only the differences gamma j minus gamma I of coefficients for decision maker attributes are identified. Typically, the coefficient associated with the first alternative, gamma 1, is normalized to 0. The conditional logit model includes only attributes that vary across alternatives, so that v n j equals x n j prime times beta. Notice that the coefficient vector beta in the conditional logit model is fixed across alternatives, while the attributes x and j vary. This is precisely the reverse of the multinomial logit model, in which coefficients vary across alternatives, but attributes do not. There's a third model that we won't talk about too much in this video, called mixed logit, that combines the multinomial and conditional logit specifications by taking v and j equal to s n prime times gamma j plus x n j prime times beta. To help us understand the difference between the multinomial and conditional logit specifications, we'll consider a simple example. Suppose that Alice wants to go fishing this weekend. She can choose to fish at the beach, from a pier, on a private boat, or on a charter boat. In this fishing example, a multinomial logit model could allow Alice's choice of where to go fishing to depend on her income, her age, and her level of fishing experience, because these do not vary depending on where she goes to fish. In contrast, a conditional logit specification could include the price and abundance of fish for each alternative mode of fishing. Maybe Alice can go fishing at the beach for free, but she's unlikely to catch anything there, while she's much more likely to catch something on a charter boat, but she has to pay $50 to be allowed onto the boat. Partial effects for the multinomial logit model are tedious to derive and difficult to interpret because the attributes Sn are common to all alternatives. A simpler approach is to consider partial effects for relative risk, namely the effects of Sn on ratios of choice probabilities, where we take one alternative as the base case. Suppose we designate the first of these as our base category. Normalizing gamma 1 equal to 0, we obtain e to the Sn prime gamma 1 equals e to the 0 equals 1. Hence, the ratio of the choice probability for alternative I to that of alternative 1 takes the following expression. And notice that these two sums from j equals 1 to capital J cancel out. This leaves us with the ratio e to the Sn gamma I divided by e to the Sn gamma 1. But with our normalization, the denominator is simply 1, so we obtain e to the Sn gamma I. Now, taking logs, it follows that the log of the ratio of choice probabilities, which is equal now to the log of e to the Sn gamma I, is simply equal to Sn prime gamma I. Therefore, the coefficient gamma ik is the marginal effect of the kth attribute on the relative probability that Alice chooses alternative I compared to alternative 1, measured on the log scale. In the fishing example, suppose that this kth attribute is income. Then, if we take fishing at the beach as the base category, gamma 2k is the effect, measured on the log scale, of a 1-unit increase in income on the probability that Alice will fish from a pier relative to the probability that she will fish from the beach. Because all of the attributes in a conditional logit model are specific to a particular alternative, it's much easier to work out partial effects for this model compared to the multinomial logit. On your problem set, you'll show that the own attribute effects for alternative j are given by pnj times 1 minus pnj times beta, while the cross attribute effects of the attributes for alternative I on the choice probability for alternative j are given by negative pnj times pni times beta, where j is not equal to I. Notice from these expressions that if increasing a particular attribute x and jk makes the decision maker more likely to choose alternative j, then it must make her less likely to choose alternative I. That's because pnj times 1 minus pnj and pnj times pni are both positive. So the sign of the own effects corresponds to those of the coefficients beta, while those of the cross effects have the opposite sign.